Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. The road stretches forward into darkness, illuminated only by twin beams that sweep across painted lines and reflective markers. Behind the wheel, hands grip worn leather, fingers adjusting constantly to compensate for the pull of wind and the camber of asphalt. Eyes blink against fatigue, muscles tense and release in patterns grown automatic through repetition. The human body, remarkable as it is, was never designed for this particular form of continuous attention. We evolved to scan horizons for threats that moved on legs, not to track painted boundaries at velocities our ancestors could never have imagined. The statistics accumulated slowly, year after year, building into monuments of loss that nobody wanted to examine too closely. Collision reports stacked in filing cabinets, each one a story of attention that wavered at precisely the wrong moment. A glance at a radio dial, a second too long, watching a child in the rearview mirror, the microsecond when exhaustion pulled eyelids closed. These weren't failures of character or intention. They were the inevitable mathematics of asking biological systems to perform tasks that exceeded their design parameters for hours at a time, day after day, across millions of simultaneous journeys. The metal boxes we built moved faster than anything in natural history, except the stoop of a hunting falcon. We paved entire continents to accommodate them, creating rivers of asphalt that channeled unprecedented masses of steel and glass through spaces measured in feet and inches. The margins for error collapsed to fractions of seconds. Reaction times that would seem instantaneous in any other context became fatally slow when closing speeds reached hundreds of feet per second. The human nervous system, lightning fast by biological standards, processed information through chemical synapses that introduced delays measured in milliseconds. Delays that translated into yards of unstoppable momentum. We tried everything we could imagine to make the system safer while keeping humans in control. We painted lines brighter, erected signs larger, installed lights that changed color in precise sequences. We wrote laws and enforced them, created licensing systems and testing protocols, engineered crumple zones and airbags and restraint systems. Each innovation saved lives, and still the numbers remain staggering. The machines weren't the problem. and neither were the people. The problem was the interface itself, the expectation that organic attention could remain perfect across billions of miles traveled, that reflexes honed for grasping branches could reliably operate controls governing tons of metal. The need emerged not from a single catastrophic failure, but from the steady accumulation of small tragedies, each one avoidable in retrospect, each one inevitable in aggregate. Engineers and dreamers began asking a question that seemed almost heretical. What if we removed the human from the equation? Not as punishment or replacement, but as recognition of a fundamental mismatch between capability and requirement. The vision that formed was both humble and audacious. Humble in its acknowledgement of human limitation, audacious in its belief that we might build something better. Long before anyone spoke seriously of machines that could drive themselves, the evidence of need accumulated in hospital emergency rooms and roadside memorials. Trauma surgeons learned to recognize the specific patterns of injury that came from particular types of collision. The frontal impact that crumpled steering columns into chests. The lateral intrusion that occurred when attention drifted across a center line. The rollover that began with an overcorrection, a panicked yank of the wheel in response to a drift that gentle adjustment could have corrected. Each pattern told a story of human limitation meeting mechanical reality. The data painted pictures that were hard to ignore once you learned to read them. Collision rates spiked during specific hours. The late afternoon when circadian rhythms dipped. The early morning when night shift workers drove home against the demands of their biology. They increased on certain days when routine broke down and attention scattered. They rose with age as reaction times lengthened, and with youth as experience remained insufficient to predict the hidden dangers lurking in ordinary situations. The patterns revealed that the problem wasn't primarily about skill or training. It was about the fundamental nature of sustained attention under conditions that evolution had never prepared us for. The distances involved created their own peculiar challenges. A vehicle traveling at highway speed crossed the length of a football field in seconds. The time required to recognize a threat, decide on a response, and execute that response consumed a significant fraction of that interval. Neural signals had to travel from eyes to brain, propagate through decision-making centers, then journey back out to muscles. Chemical reactions had to occur at synapses. Muscle fibers had to contract. Mechanical linkages had to overcome inertia. By the time all these steps completed, the world had already moved forward by dozens of yards. The buffer between recognition and consequence remained thin to the point of translucence. We asked drivers to maintain this alertness for hours without break, monitoring dozens of variables simultaneously. Speed and spacing and lane position, the behavior of adjacent vehicles and the condition of the road surface, traffic signals and signs and the movements of pedestrians, weather conditions and visibility, and the mechanical state of their own vehicle. The cognitive load would have been extraordinary under any circumstances. We imposed it while people were tired from work, distracted by conversation, anxious about destinations, angry about delays, sad about losses, celebrating victories, or simply lost in the ordinary drift of human thought. The need wasn't theoretical or projected. It existed in the present tense, accumulating every day in forms both dramatic and mundane. It lived in the father who arrived home later than planned because traffic had stopped for a collision ahead. It lived in the mother who white-knuckled her way through a snowstorm, arriving safe but exhausted. It lived in the elderly couple who began curtailing their independence because nighttime driving had become too stressful. It lived in the teenager who hadn't yet developed the pattern recognition that comes only through years of exposure to near misses and close calls. The dream of autonomous vehicles wasn't born from technological enthusiasm alone. It grew from the recognition that we had built a system that exceeded human capacity, and that the cost of maintaining it in its current form was being paid in measures too heavy to sustain. The idea arrived long before the technology to implement it existed, appearing first in the realm of imagination rather than engineering. Writers and illustrators sketched vehicles that piloted themselves, guided by unseen forces through futures where human attention could turn to matters more engaging than the mechanics of navigation. These weren't technical proposals, but rather explorations of possibility, asking what life might become if the burden of constant vigilance could be lifted. The images showed passengers reading, conversing, sleeping, while their vehicles threaded through traffic with inhuman precision. The fantasy appealed not because people disliked driving, but because they recognized how much of it felt like necessary tedium rather than genuine engagement. The earliest practical experiments came from unexpected directions. Before anyone thought seriously about autonomous automobiles, engineers worked on systems to guide vehicles along predetermined paths for industrial purposes. Factories needed materials moved from one station to another without tying up human workers for the transport. Warehouses required inventory shuttled between storage and loading docks. These environments offered controlled conditions, flat floors, known obstacles, defined routes. The vehicles that emerged moved slowly, following buried wires that generated electromagnetic fields their sensors could detect. They weren't intelligent in any meaningful sense. They simply traced invisible rails laid into the ground beneath them, stopping when their primitive sensors detected obstructions. The leap from following a wire to navigating open roads seemed impossibly vast, but the principle planted seeds. If a machine could sense its position relative to a guide path, perhaps it could eventually sense position relative to road boundaries. If it could detect obstacles and stop, perhaps it could eventually detect obstacles and avoid them. The progression seemed logical in theory, though the gap between theory and practice yawned wide enough to swallow decades of effort. The controlled environment of a factory floor bore little resemblance to public roads, where variables multiplied beyond easy prediction. Military applications drove early development in ways that would only become clear much later. The desire to move supplies and equipment without risking operators in dangerous territories motivated research into remote control and autonomous navigation. Test vehicles rolled across proving grounds, their progress measured in feet per minute rather than miles per hour. They bumped into barriers, lost their way when lighting conditions changed, confused shadows with obstacles and obstacles with shadows. Each failure provided data. Each marginal success suggested that the problem, while difficult, might not be impossible. The sensors available in that era possessed severe limitations. They could detect the presence or absence of objects, but struggled with identification and classification. A sensor might register that something existed in the vehicle's path, but couldn't distinguish between a cardboard box and a concrete barrier. Range measurements remained crude, prone to errors that cascaded through any system trying to make navigation decisions. Processing power existed in forms that seem almost comical now. Rooms full of equipment to accomplish computations that modern devices complete in microseconds. The vision of autonomous vehicles existed clearly in imagination, but the tools to realize that vision remained stubbornly out of reach. The conceptual framework for autonomous navigation drew from multiple sources, including fields that seemed unrelated to vehicles at all. Researchers studying how insects navigated began identifying principles that didn't require complex intelligence. Desert ants found their way home across featureless sand by tracking the angle of sunlight and counting their steps, building an internal map through dead reckoning. Bees communicated the location of food sources through precise dances that encoded direction and distance. These biological systems suggested that navigation didn't necessarily require understanding in any deep sense. It required only sufficient information and appropriate responses to that information. Engineers borrowed concepts from aviation, where instruments had long replaced human senses for certain aspects of control. Autopilot systems kept aircraft level and on heading, maintaining altitude without constant manual input. They didn't understand flight or weather or strategy, but they could hold parameters steady with a precision that freed human pilots to focus on higher-level decisions. The parallel to automotive navigation seemed clear, though the specifics differed dramatically. Aircraft traveled through three-dimensional space with relatively few obstacles and generous margins for error. Ground vehicles shared crowded two-dimensional planes where mistakes measured in inches could produce catastrophic results. The concept of feedback loops became central to early thinking about autonomous control. A system could measure its deviation from a desired state, then apply corrections proportional to that deviation. Temperature controls already worked this way. Thermostats measuring difference between current and target temperatures, then activating heating or cooling systems to minimize that gap. The same principle could theoretically govern steering. Measure deviation from desired path, calculate correction needed, adjust steering angle. The devil lurked in complications that seemed minor until you attempted implementation. How did you define the desired path? How accurately could you measure current position? How did you account for the delay between sensing and action? Demonstrations in controlled environments produced moments of success that fed optimism. A vehicle following a wire around a test track proved the basic concept worked under ideal conditions. Sensors detecting obstacles and triggering stops showed that machines could respond to their environment. Remote control systems proved that vehicles could operate without onboard human operators. Each piece existed independently, functioning within narrow parameters. The challenge lay in integration, combining these elements into systems robust enough to handle the endless variations present in real-world conditions. The enthusiasm of early researchers sometimes outpaced their results by margins that would seem embarrassing in retrospect. Predictions about timelines to full autonomy assumed that engineering challenges would yield to sustained effort in predictable ways. They underestimated how many edge cases existed, how many situations would prove subtly different from anything anticipated during design. A system that worked perfectly for thousands of test miles might encounter something unexpected in the next 100 yards, a pattern of shadows that resembled lane markings, a reflection that registered as an obstacle, an ambiguous situation where even human observers couldn't agree on the correct interpretation. The dream remained vivid and compelling, but the path to realization stretched far longer than those early visionaries imagined. The progress happened in layers, each generation of researchers building on foundations laid by predecessors who had struggled with problems that seemed almost quaint in retrospect. The first layer involved simply getting vehicles to perceive their surroundings in any reliable way. Early optical sensors could distinguish light from dark, but they struggled with gradations, with textures, with the difference between a white line on dark pavement and a bright reflection on wet asphalt. The analog signals they produced flickered and drifted, requiring constant calibration to maintain even marginal accuracy. Engineers spent thousands of hours teaching systems to recognize features that human drivers identified instantly and unconsciously. Computing power accumulated according to patterns that became law through observation rather than theory. The processors available each year could handle roughly twice the calculations of those from the previous year, while occupying half the space and consuming half the power. What began as refrigerator-sized machines controlling simple robots shrank to briefcase-sized units, then to boxes that fit on shelves, then to components that disappeared into dashboard spaces. The transformation wasn't merely quantitative. The increase in processing capacity enabled qualitatively different approaches to problems that had seemed intractable when computation budgets remained constrained. The mathematical frameworks for understanding control systems matured through decades of application in fields ranging from industrial automation to aerospace. Engineers developed formal methods for analyzing stability, for predicting how systems would respond to disturbances, for ensuring that feedback loops converge toward desired states, rather than oscillating wildly or diverging catastrophically. These tools didn't solve the problems of autonomous vehicles directly, but they provided languages for describing those problems precisely, and techniques for validating that proposed solutions would behave safely under specified conditions. Sensor technology evolved along multiple parallel tracks. Radar systems borrowed from aviation and adapted for automotive use could measure distances and velocities to objects regardless of lighting conditions. Cameras increased in resolution while decreasing in size and cost, eventually capturing color images detailed enough for sophisticated analysis. Laser-based ranging systems swept beams across their surroundings, measuring time of flight to build point clouds representing three-dimensional space. Ultrasonic sensors detected nearby obstacles through sound waves. GPS receivers determined absolute position by triangulating signals from orbiting satellites. Each sensor type had particular strengths and weaknesses, seeing some aspects of the environment clearly while remaining blind to others. The accumulation happened in research laboratories and proving grounds scattered across continents. Universities launched programs focused on robotics and artificial intelligence. Defense departments funded projects aimed at autonomous logistics and reconnaissance. Automotive manufacturers established advanced engineering groups to explore technologies that might become relevant in future decades. The work remained fragmented, each group pursuing approaches shaped by their particular constraints and objectives. Occasional conferences allowed researchers to share results, revealing both convergence on certain solutions and persistent disagreement about fundamental approaches. The field lacked consensus on whether autonomous vehicles represented a near-term practical goal or a distant aspiration requiring breakthroughs not yet visible on the horizon. The challenge of perception proved deeper than initially apparent. It wasn't enough to detect objects. The system needed to classify them, to distinguish between categories that required different responses. A plastic bag tumbling across the road posed no threat and could be safely ignored. A cardboard box might be ignored or might conceal something solid. A tire fragment demanded avoidance. A small animal required stopping if possible, swerving if necessary. A child always required maximum emergency response. Teaching systems to make these distinctions reliably consumed enormous research effort, because the differences that seemed obvious to human observers often reduced to subtle patterns in sensor data. The accumulation of edge cases presented a particular form of frustration. Each time a system reached a level of reliability that seemed impressive, testing would reveal new situations where it failed in unexpected ways. Shadows cast by overpasses created sensor patterns similar to solid barriers. Raindrops on camera lenses scattered light in ways that confused image analysis. Fog absorbed and scattered laser beams, making distance measurements unreliable. Bright sunlight shining directly into sensors could blind them temporarily. Snow obscured lane markings and covered signs. Construction zones reconfigured roads in ways that contradicted map data. Each scenario required specific solutions, and the list of scenarios never seemed to reach completion. Machine learning emerged as a complementary approach to explicit programming. Instead of writing rules for every possible situation, researchers fed systems vast collections of examples labeled by human observers. The systems learned to identify patterns that distinguished one category from another, developing internal representations that sometimes bore little resemblance to how human programmers would have approached the problem. A system trained on thousands of images of pedestrians could eventually recognize pedestrians in new images with remarkable accuracy, even in poses and clothing and lighting conditions it had never seen before. The approach worked impressively well for some tasks, while revealing new forms of brittleness for others. Data became a resource as valuable as algorithms or computing power. Training sophisticated systems required millions of examples captured under diverse conditions. Companies and research groups dispatched fleets of instrumented vehicles to drive endless miles, recording sensor data synchronized with human annotations, describing what the sensors were perceiving. The footage accumulated in vast databases, terabytes of information, documenting the visual and geometric properties of roads and traffic and weather conditions. The collection effort represented enormous investment, but without sufficient data, even the most sophisticated algorithms remained unable to learn the patterns necessary for reliable operation. The timeline from early concepts to practical implementations stretched across decades, measured not in steady increments, but in sudden advances separated by long plateaus. A new sensor technology would enable approaches that had been purely theoretical. A breakthrough in algorithms would make problems that seemed impossibly difficult suddenly tractable. An increase in computing power would allow real-time analysis of data volumes that previously required hours of offline processing. The accumulation wasn't smooth or predictable, but retrospectively, it traced a path from crude experiments to systems approaching viability. The dream that had seemed impossibly distant began to resolve into something that might, with continued effort, become reality within lifetimes of those who had initiated the pursuit. The physical systems that translate decisions into motion existed long before anyone considered autonomous operation, but adapting them for computer control required rethinking assumptions built into decades of design. Traditional steering mechanisms connected driver input directly to wheel angle through hydraulic or mechanical linkages that provided feedback. The resistance you felt turning the wheel communicated information about tire grip and road conditions. Removing the human from this loop meant preserving the control path while eliminating the feedback channel that drivers used unconsciously to modulate their inputs. Electric motors replaced hydraulic pumps, providing steering assistance that could be commanded digitally with precision measured in fractions of degrees. Braking systems underwent similar transformation. Conventional brakes translated pedal pressure into hydraulic force distributed among wheels according to fixed ratios designed to prevent lockup and maintain stability. Anti-lock systems already used electronic control to modulate brake pressure faster than human reflexes allowed, pulsing individual wheel brakes to maintain traction during emergency stops. Autonomous operation required extending this principle, allowing computers to command specific braking forces at each wheel independently. The mechanical components, calipers and rotors and pads, remain similar to their traditional counterparts, but the control architecture shifted from human input, amplified by simple systems, to computer commands executed by sophisticated actuators. Throttle control migrated from cables connecting pedals to carburetors through electronic systems that interpreted pedal position as requested power, to interfaces where computers could directly command acceleration without any pedal input at all. The internal combustion engine's complexity created challenges here. It couldn't instantly produce arbitrary power levels the way an electric motor could. Fuel delivery and ignition timing and valve operation all required coordination across mechanical systems with their own response characteristics. Electronic engine management systems had already computerized much of this coordination, but they expected inputs that changed smoothly according to human driving patterns. Autonomous control needed to integrate with these systems, requesting acceleration profiles that the engine could deliver without roughness or inefficiency. The transition to electric powertrains simplified some aspects while introducing new considerations. Electric motors responded to throttle commands with immediacy that combustion engines couldn't match, producing torque instantly across their operating range. This responsiveness made precise speed control easier, eliminating the lag between requesting acceleration and feeling the vehicle respond. But it also meant that control algorithms needed careful tuning to avoid abruptness that would be uncomfortable for passengers. The smooth modulation that human drivers provided naturally required careful programming when computers assumed control. Sensor mounting presented mechanical challenges that seemed mundane, but proved critical. Cameras needed clear views unobstructed by dirt or water, requiring positions where airflow would keep lenses clean, and heating elements could prevent fog or ice accumulation. Radar and laser sensors needed rigid mounting to prevent vibration from misaligning their beams, introducing errors that would accumulate over time. Wiring harnesses had to route signals from sensors distributed around the vehicle to centralized processors without picking up electromagnetic interference from the motors and power systems generating fields strong enough to corrupt delicate signals. Every mechanical decision cascaded through the system, affecting reliability and performance in ways that wouldn't become apparent until vehicles accumulated thousands of miles under real conditions. The redundancy requirements for autonomous systems exceeded anything present in conventional vehicles. When a human driver controlled the vehicle, they provided backup for any single component failure. If one sensor failed, human eyes continued seeing. If one control system malfunctioned, human reflexes could compensate. Removing the human meant building redundancy into the machine itself. Critical sensors needed duplicates or backups using different physical principles. If a camera failed, radar might provide sufficient information to reach safety. If one processor crashed, another needed to assume control seamlessly. The mechanical complexity multiplied as designers added layers of backup systems, each one increasing weight and cost and potential failure points, even as it improved overall reliability. Power distribution became critical in ways it never had been for human-driven vehicles. Traditional electrical systems could tolerate momentary interruptions. Lights might flicker, radio might reset, but the driver maintained control through purely mechanical or hydraulic connections. Autonomous vehicles required uninterrupted power to sensors and computers and actuators, because any gap in processing would leave the vehicle effectively blind and paralyzed. Battery systems provided backup power separate from the main electrical system. Capacitors stored energy to bridge microsecond gaps when switching between power sources. Multiple independent power buses ensured that failure in one circuit couldn't cascade to disable all systems simultaneously. The physical packaging of components required compromise between competing demands. Processors generated heat that needed dissipation without excessive noise from cooling fans. Sensors needed exposure to the environment while remaining protected from impacts and weather. Wiring needed routing that avoided interference and mechanical stress while remaining accessible for service. The interior space that might have contained cargo or additional seating instead housed computer enclosures and power distribution systems. Early autonomous vehicles resembled research platforms more than consumer products, with exposed equipment racks and bundles of cables that would never survive the aesthetic or durability requirements of production vehicles. Calibration procedures developed into elaborate rituals necessary to maintain system accuracy. Sensors mounted to vehicle bodies experienced vibration, temperature changes, and mechanical stress that could shift their alignment by fractions of degrees. Small angular changes that translated into significant errors in measured positions of distant objects. Systems needed to verify their calibration continuously, comparing data from multiple sensors to detect when one had drifted out of specification. Some calibration happened automatically through clever algorithms that exploited redundant measurements. Other aspects required manual intervention, technicians using specialized equipment to verify that sensors reported positions that matched known reference targets. The mechanical reliability standards for autonomous vehicles dwarfed those of conventional automotive engineering. A component failure that would merely inconvenience a human driver, a broken mirror, a malfunctioning turn signal, a tire pressure sensor reading incorrectly, could completely disable an autonomous system that depended on that component for situation awareness or communication with other road users. Manufacturers learned to design systems that degraded gracefully, maintaining reduced functionality when individual components failed, rather than shutting down entirely. A vehicle that lost one camera might restrict itself to lower speeds and simpler road conditions where its remaining sensors provided adequate coverage. The mechanical systems needed to anticipate partial failures and provide pathways to safety, even when optimal operation became impossible. The infrastructure that autonomous vehicles would eventually navigate had accumulated over more than a century of development, built by thousands of jurisdictions following guidelines that evolved independently and sometimes contradicted each other. Road markings followed conventions that were consistent within regions but varied between states and countries. Yellow lines meant different things in different places. Solid versus dashed patterns encoded rules that weren't universal. Colors and patterns and placements all carried meanings that human drivers learned through cultural transmission, but machines needed to decode from specifications that didn't always exist in written form. Traffic signals presented particular challenges because their physical implementations varied wildly, while their meanings remained relatively consistent. Some jurisdictions mounted signals vertically, others horizontally. Some used circular lights, others used arrows, some used both. The shades of red and green and yellow weren't standardized. Different bulb types and lens colors produced variations that human eyes compensated for unconsciously, but that cameras had to distinguish reliably under all lighting conditions. Position on the signal head conveyed meaning in some places, but not others. The timing of transitions between states followed patterns that varied by intersection, time of day, and detected traffic conditions. Sign design had evolved toward standardization over decades, driven partly by recognition that consistency improves safety and partly by economic efficiency in manufacturing and installation. Shapes carried meaning independent of text. Octagons always meant stop, triangles meant yield, rectangles provided information, colors encoded categories, red for mandatory instructions, yellow for warnings, green for navigation information, blue for services. But the text on signs assumed literacy in specific languages. The symbols assumed familiarity with cultural conventions, and the placement followed guidelines that allowed considerable variation in implementation. A system needed to detect signs from sufficient distance to respond appropriately, while distinguishing official regulatory signs from commercial signs or parked vehicles bearing similar colors and shapes. Pavement markings degraded over time, wearing away under traffic and weather until they became barely visible even to human observers. Maintenance schedules varied by jurisdiction and budget, creating conditions where critical navigation information might be clear on one section of road and nearly absent on another. Snow-covered markings entirely for months in some regions. Construction zones obscured or contradicted permanent markings with temporary configurations. The rules about what markings meant, when crossing them was prohibited versus discouraged versus allowed, involved subtleties that required understanding context beyond the markings themselves. The push for standardization came from multiple directions simultaneously. Automotive manufacturers recognized that autonomous systems would need to operate across jurisdictions, making extreme variation in infrastructure a barrier to deployment. Highway departments saw opportunities to improve safety through more consistent signaling and marking. Technology companies developing autonomous systems advocated for specifications that their sensors and algorithms could reliably interpret. The process involved negotiation between groups with different priorities and different timelines for change. Infrastructure upgrades required years of planning and funding and implementation, while technology development moved faster, creating pressure to make systems work with existing conditions, even as those conditions slowly evolved. The communication protocols between vehicles and infrastructure emerged as another domain requiring standardization. Early proposals imagined roads broadcasting information directly to vehicles: traffic signal timing, speed limits, construction warnings, weather conditions. This required agreement on radio frequencies, data formats, encryption methods, and authentication systems to prevent malicious actors from sending false information. The benefits seemed clear. Vehicles could know signal timing before the light became visible, could receive warnings about conditions beyond sensor range, could coordinate with each other to optimize traffic flow. But deployment required coordinating changes across disparate systems managed by different entities with different budgets and upgrade cycles. Map data represented perhaps the most complex standardization challenge. Autonomous vehicles needed maps far more detailed than those designed for human navigation. Lane-level accuracy wasn't sufficient. Systems needed to know the precise geometry of road surfaces down to centimeter-level accuracy, the positions of every sign and signal, the boundaries of permitted driving areas at every point. Creating these maps required massive data collection efforts, driving every road with survey-grade sensors, then processing the raw data to extract relevant features. Maintaining the maps required detecting when construction or permanent changes altered road configuration. Different organizations created maps using different methods and formats, making interoperability difficult. The standardization of testing and validation procedures became critical as autonomous vehicles approached deployment. How could manufacturers demonstrate that their systems were safe enough for public roads? What scenarios needed testing? And how many repetitions of each scenario were required to achieve statistical confidence? Regulatory bodies struggled to define appropriate standards when the technology itself remained in development. Too stringent requirements might prevent deployment of systems that were safer than human drivers. Too lax requirements might allow dangerous systems to reach public roads. The problem had no clear precedent. Previous vehicle safety regulations addressed mechanical failures and crash protection, not decision-making systems whose behavior emerged from millions of lines of code. Professional organizations and industry consortiums formed to develop shared standards and best practices. Engineers from competing companies met to discuss sensor specifications and communication protocols and testing methodologies. The collaboration happened awkwardly at first, participants trying to find balance between sharing information necessary for industry-wide progress and protecting proprietary advantages. But the recognition grew that certain problems required collective solutions. A vehicle from one manufacturer needed to understand signals sent by another manufacturer's vehicle. Infrastructure investments in communication systems needed to support vehicles from all manufacturers. The standardization didn't eliminate competition, but it created foundations that all competitors could build on. The process revealed tensions between perfect standardization and rapid innovation. Lock in standards too early, and you prevent improvements based on new understanding. Wait too long for standardization, and you end up with incompatible systems that can't communicate or share infrastructure. The solution involved layers, standardizing interfaces and data formats while allowing flexibility in implementation details, defining minimum requirements while permitting enhanced capabilities. The work proceeded in parallel with technology development, each informing the other, creating gradually more detailed specifications as practical experience revealed what standards needed to address. The change arrived not through sudden announcement, but through gradual accumulation of capabilities that seemed distinct until retrospect revealed their connection. Vehicles gained the ability to maintain lane position on highways, keeping themselves centered between painted lines through gentle steering adjustments that required no driver input. This wasn't autonomy in any complete sense. It demanded human attention, remain focused on the road, hands hovering near the wheel, ready to resume control at any moment. But it represented delegation of a specific task, the vehicle handling the continuous micro-corrections that highway driving required, while the human monitored overall situation and strategy. Thousands of drivers experience this assistance daily without considering it a step toward full autonomy. Adaptive cruise control evolved from simple speed maintenance to systems that adjusted following distance automatically, accelerating and braking to maintain safe spacing from vehicles ahead. The sensors required for this capability, radar units measuring distance and relative velocity to forward traffic, became standard equipment on vehicles across price ranges. Drivers who activated these systems experienced a form of longitudinal control where the vehicle managed its own speed in response to traffic conditions. Combined with lane keeping, this created sustained periods where the vehicle controlled both steering and speed, though always with the understanding that human takeover might be required at any moment. Parking assistance systems demonstrated that vehicles could navigate complex low-speed maneuvers without human control of steering. Sensors measured available space. Processors calculated trajectories. Actuators executed precise steering patterns to guide vehicles into parking spots that drivers found challenging. The capability seemed isolated, a convenience feature unrelated to broader autonomy. But it established precedent and built public comfort, with vehicles controlling themselves in certain contexts. It also proved that the mechanical systems could execute computer commands reliably enough for everyday use by consumers who understood nothing of the underlying technology. Emergency braking systems watched forward sensors continuously, calculating collision risks and priming brake systems for maximum effectiveness. When they detected imminent impact that the driver hadn't responded to, they applied brakes automatically with forces humans rarely generated, even in emergencies. These interventions happened in fractions of seconds, too quickly for drivers to perceive the system's decision-making process. The vehicle had detected danger, evaluated options, and taken protective action without consultation. Lives were saved through these interventions, creating positive associations with automated decision-making, even among people skeptical of broader autonomy. The transition happened in living rooms and driveways rather than through dramatic demonstrations. Features marketed for convenience and safety rather than autonomy gradually accustomed millions of people to vehicles that made decisions and took actions without explicit human commands. The systems remained limited in capability and scope. They operated only in specific situations, only at certain speeds, only when conditions fell within parameters their designers had anticipated. But they normalized the concept of the vehicle as active participant rather than passive tool. The steering wheel still expected human hands, but those hands were learning to trust that the vehicle could handle certain responsibilities competently. The legal frameworks struggled to keep pace with capabilities that advanced faster than legislation could evolve. Laws written for human-driven vehicles assumed that a licensed operator maintained constant control and bore responsibility for the vehicle's actions. The intermediate systems confused this clarity. If a lane-keeping system failed to detect a sharp curve and the vehicle departed the road, who bore responsibility? The driver who wasn't controlling steering, the manufacturer who provided the system? The answer remained unsettled, varying by jurisdiction and specific circumstance. Liability concerns created pressure for clear distinctions between assistance systems that supported human drivers and autonomous systems that replaced them. Insurance models based on centuries of actuarial data measuring human driver risk found themselves confronting vehicles whose behavior was shaped by software updates and sensor calibrations. A vehicle might perform differently after a software update than before, altering its risk profile in ways that traditional underwriting didn't accommodate. Companies began collecting detailed data about how drivers used assistance features, how often systems intervened, how frequently drivers overrode system decisions. This granular measurement of behavior enabled more sophisticated risk assessment, but raised privacy concerns about the surveillance required to generate such detailed records. The vocabulary people used to describe these systems revealed conceptual confusion. Manufacturers chose marketing terms carefully, trying to communicate capability without overstating it or creating false confidence. But the names given to features, autopilot, co-pilot, self-driving, autonomous, assisted driving, carried connotations that didn't always match technical reality. Drivers developed mental models of system capabilities based on names and marketing materials, rather than detailed understanding of actual functions and limitations. Tragic incidents occurred when driver expectations exceeded system capabilities, when people trusted assistance systems to handle situations beyond their design parameters. Professional drivers watched these developments with mixed feelings. Truck drivers and taxi operators and delivery personnel saw their livelihoods potentially threatened by technology that might eventually replace human operators. Some embraced the assistance features, finding that they reduced fatigue and made long shifts more bearable. Others resisted, viewing the technology as surveillance systems that monitored their every action, or as threats to the skill and judgment they developed over years of professional practice. The transition wasn't just technical. It touched on questions of human purpose and economic security, and the value society placed on expertise. The silent transition continued even as debate about autonomous vehicles intensified. While experts argued about timelines to full autonomy and appropriate regulatory frameworks, millions of vehicles on roads worldwide were already operating with substantial automated capabilities. The line between human driving and machine driving had blurred into a gradient, with vehicles occupying various points along a spectrum from full manual control to nearly complete automation. The future arrived not through revolutionary announcement, but through incremental steps, each one seeming minor until their cumulative effect became impossible to ignore. The dream of autonomous vehicles was being realized in pieces, scattered across features and capabilities that most people didn't connect into a coherent vision of where the progression was heading. The roads themselves carried information encoded in their physical structure, patterns that had evolved over decades to communicate with human perception. The radius of a curve warned drivers how sharply they needed to turn. The width of lanes balanced efficient use of space against the margin for error human control required. The banking of turns helped vehicles maintain traction at design speeds. All of this infrastructure assumed human operators processing visual information and applying learned intuition about vehicle dynamics. Adapting it for machine perception required either teaching machines to read the same cues humans used, or modifying infrastructure to communicate in ways machines could interpret more reliably. Painted markings served as the primary navigation aid, but their effectiveness varied with conditions that machines struggled to compensate for as naturally as humans did. Fresh paint reflected clearly in headlight beams and showed up distinctly in camera images. Worn paint barely contrasted with pavement, requiring algorithms to interpolate between faint marks or rely on other information sources. Reflective markers embedded in pavement helped under some lighting conditions, but created glare under others. The various marking materials, paint, thermoplastic, tape, reflected light differently, appearing consistent to human eyes, but creating different sensor signatures that algorithms had to account for. Rain filled the texture of pavement and markings alike, reducing contrast to levels where even sophisticated image processing struggled to identify lane boundaries reliably. The positioning of infrastructure elements followed guidelines rather than rigid specifications, allowing variation that rarely confused human drivers but complicated machine interpretation. Signs were supposed to appear on the right side of the road, but sometimes appeared on the left or overhead, sometimes preceded by advance warning signs, and sometimes not. Signal lights were supposed to be visible from specific distances, but trees or buildings sometimes obstructed them until vehicles reached closer than ideal. Speed limits were supposed to change only at posted signs, but local practice sometimes involved unposted changes that drivers learned through experience or enforcement. The flexibility that had allowed infrastructure to adapt to local conditions created ambiguities that autonomous systems needed additional information to resolve. GPS systems provided absolute position information accurate to within several meters under good conditions. But this precision proved insufficient for lane-level navigation on highways where lanes were only a few meters wide. Differential GPS systems improved accuracy by comparing measurements against reference stations at known locations, reducing errors to centimeters under ideal conditions. But satellite signals could be blocked by buildings or bridges or tunnels, could be degraded by atmospheric conditions, could be spoofed or jammed by interference, deliberate or accidental. Autonomous systems learn to fuse GPS data with other information sources, using the absolute positioning as one input among many, rather than relying on it exclusively. High-definition maps emerged as crucial infrastructure, though they weren't physical infrastructure in traditional sense. These databases contained geometric descriptions of road surfaces accurate to centimeter level, positions of every lane marking and sign and signal, information about speed limits and turn restrictions and right-of-way rules. Creating them required survey vehicles driving every road while recording precise measurements that were later processed to extract relevant features. Maintaining them required detecting when roads changed and updating the database accordingly. The maps represented enormous investments in data collection and processing, and they created new dependencies. Vehicles needed map data to navigate, making the availability and accuracy of maps critical to autonomous operation. Vehicle-to-infrastructure communication promised to enhance autonomous operation by allowing roads to broadcast information directly to vehicles. Traffic signals could transmit their current state and timing patterns, eliminating uncertainty about whether a distant light was red or green. Construction zones could advertise their presence and extent before vehicles reached them. Weather stations could report conditions that sensors might detect too late to respond optimally. The concept seemed straightforward, but implementation required installing communication equipment at thousands of intersections and work zones, establishing reliable power and network connectivity, developing protocols for data formats and security, and maintaining systems dispersed across vast geographic areas. The cellular networks that had become ubiquitous for personal communication offered potential infrastructure for autonomous vehicles to communicate with remote servers and with each other. Vehicles could upload sensor data to be processed by powerful computers in data centers, receiving back driving decisions calculated using resources far exceeding what could fit on board. They could share information about road conditions and traffic and hazards, creating collaborative awareness that benefited all equipped vehicles. But cellular networks had limitations. coverage gaps existed in rural areas and tunnels. Latency Between sending data and receiving responses introduced delays that could be critical for time-sensitive decisions. Bandwidth constraints limited how much data could be transmitted continuously from multiple vehicles. Dedicated short-range communication systems were designed specifically for vehicle-to-vehicle and vehicle-to-infrastructure interaction. Operating on reserved radio spectrum, these systems allowed vehicles in proximity to exchange position and velocity and intention information multiple times per second. A vehicle approaching an intersection could broadcast its presence to others nearby, receiving similar broadcasts that allowed it to build awareness of traffic it couldn't yet see directly. The technology worked well in testing, but required widespread adoption to realize its benefits. Isolated, equipped vehicles gained little advantage when most surrounding traffic remained invisible to the communication system. The challenge of infrastructure investment fell unevenly across jurisdictions with vastly different resources and priorities. Wealthy urban areas could afford to instrument intersections with communication equipment and maintain high-definition map databases updated continuously. Rural regions operating on limited budgets struggled to maintain basic road surfaces and replace faded signs, much less invest in advanced infrastructure for vehicles that might not arrive for years. This created risk of a two-tier system where autonomous vehicles could operate fully in some areas, but faced degraded capability or couldn't operate at all in others. The equity implications raised questions about whether advanced transportation technology would reduce or amplify existing disparities. Private investment in infrastructure competed and complemented public funding. Technology companies developing autonomous systems had incentive to deploy infrastructure that enabled their vehicles to operate more capably. Some proposed business models where infrastructure deployment was tied to service provision. Companies would instrument certain areas in exchange for preferential access or exclusive rights to operate autonomous services there. These arrangements raised concerns about privatization of public road systems and the precedent of allowing private entities to control access to transportation infrastructure. The negotiations between public agencies responsible for roads and private companies developing autonomous technology revealed tensions between innovation incentives and public interest considerations that would take years to resolve satisfactorily. The vision of autonomous vehicles developed simultaneously across continents, shaped by different driving cultures and regulatory philosophies and infrastructure conditions that created distinct approaches to common problems. In regions where roads followed organic patterns laid down over centuries, where medieval street grids persisted beneath modern traffic, the challenge of navigation demanded systems capable of handling narrow passages and ambiguous right-of-way, and pedestrians who moved through spaces with assumptions about vehicle behavior rooted in local custom. The algorithms developed for wide American highways with clear lane markings proved insufficient for European city centers, where painted lines often didn't exist, and traffic flow followed unwritten rules, negotiated moment by moment. Asian megacities presented density challenges that exceeded anything found elsewhere, with traffic volumes that compressed vehicles into formations requiring coordination and trust that human drivers managed through subtle communication, eye contact and hand gestures, and incremental position adjustments that signaled intention without formal traffic control. Teaching machines to participate in this collaborative negotiation required understanding cultural context as much as traffic engineering. The personal space boundaries that defined comfortable following distances varied between cultures, making systems tuned for one region feel timid or aggressive when operating in another. Speed preferences, lane discipline, yielding behavior, all varied in ways that autonomous systems needed to accommodate to operate smoothly within local traffic patterns. Weather conditions across different climates created requirements that couldn't be satisfied by single sensor configurations. Tropical regions experienced rain intensities that overwhelmed camera systems designed for temperate zones. Arctic conditions created ice accumulation on sensor surfaces and temperature extremes that affected electronics differently than mild climate testing had revealed. Desert environments subjected vehicles to dust that infiltrated seals and abrasive particles that wore sensor windows faster than designers had anticipated. Each climate zone revealed new edge cases, new combinations of conditions that testing in other regions hadn't prepared systems to handle. The global deployment of autonomous technology required either accepting regional limitations or developing systems robust enough to operate across the full range of human habitation. Regulatory approaches diverged between regions that embraced testing of experimental technology on public roads and those that demanded extensive private proving ground validation before allowing any public exposure. Some jurisdictions created special zones where autonomous vehicles could operate under relaxed restrictions, accelerating development, but creating questions about what would happen when vehicles needed to transition between zones with different rules. Others maintained that public roads required proven safety before experimental systems could use them, slowing local development, but potentially preventing incidents that might set back public acceptance. The lack of international coordination created patchwork conditions where vehicles approved in one country couldn't legally operate in another. The knowledge sharing between groups working on autonomous vehicles across the globe happened through academic publications and conferences and occasional collaborative research projects, but much remained proprietary and protected. Companies competing for commercial advantage had limited incentive to share breakthroughs that might provide competitive advantage. This slowed overall progress compared to what fully open collaboration might have achieved, but it also created diversity in approaches that prevented the entire field from committing to architectures that might prove inadequate. Multiple groups attacking the same problems from different directions increased the chance that someone would find solutions that prove generalizable, even if it meant redundant effort and inefficient distribution of resources. The transfer of technology between regions happened unevenly, with some innovations spreading rapidly while others remained trapped by local conditions or regulatory barriers. Sensor technologies developed for one market found applications in others once they became commercially available, but the software architectures and decision-making approaches proved harder to transfer. A system trained on millions of miles in one country's traffic conditions didn't necessarily perform well when deployed elsewhere without substantial retraining. The data collection required to adapt systems to new environments represented significant investment, creating barriers that favored large organizations with resources to instrument fleets across multiple continents. Language differences created unexpected challenges for systems that needed to read text on signs and understand regional variations in traffic symbols. A stop sign might use different words in different countries, might be accompanied by text in multiple languages, might be formatted according to local conventions that machines needed to learn separately for each region. The shapes and colors of signs followed broadly similar principles globally, but varied in details that complicated recognition algorithms. Some regions used symbolic signs almost exclusively to accommodate populations speaking multiple languages, while others relied heavily on text, assuming shared literacy. Training systems to operate globally meant accounting for this variability while maintaining reliability in recognizing critical safety-related information. The economics of autonomous vehicle development created pressure toward consolidation and partnership across international boundaries. The investment required to bring systems to market exceeded what most individual companies could justify, leading to joint ventures and collaborative development agreements between manufacturers on different continents. These partnerships allowed sharing of development costs and pooling of data collected across different regions, but they also created complex intellectual property arrangements and raised questions about technology, transfer, and national security implications when autonomous vehicle systems incorporated components from international supply chains. Cultural attitudes toward automation and trust in technology varied in ways that affected adoption prospects independent of technical capability. Some societies embraced automated systems enthusiastically, viewing them as progress and willing to accept early-stage limitations in exchange for being first to access new capabilities. Others maintained skepticism rooted in cultural values, emphasizing human judgment, or recent experiences with technology failures that had undermined confidence. The pace of deployment would be shaped not just by technical readiness, but by social acceptance that varied between regions for reasons having little to do with the technology itself. The infrastructure investments required for full autonomous deployment created opportunities for developing regions to leapfrog intermediate stages that wealthier countries had already committed to. Just as some regions skipped landline telephone networks and moved directly to cellular, there was potential for newer road systems to incorporate communication capabilities and standardized design elements from the beginning, rather than retrofitting them onto legacy infrastructure. This could position some regions to support autonomous vehicles more effectively than areas with mature but less optimized road networks. The global competition to attract autonomous vehicle testing and deployment created incentives for infrastructure investment that might accelerate adoption in unexpected locations, reshaping assumptions about which regions would lead in implementation of the technology. The question of how autonomous vehicles should behave in impossible situations forced consideration of ethical frameworks that human drivers navigated through instinct and improvisation. The classic formulation involved vehicles facing unavoidable collisions where every action produced harm. Should the system protect its occupants at others' expense, distribute risk equally, minimize total casualties, or follow some other principle? Human drivers in such situations acted without time for ethical deliberation, their responses shaped by reflexes and circumstances rather than philosophical principle. But programming autonomous systems required making choices explicit, encoding priorities that would determine behavior in situations where perfect outcomes remained impossible. The challenge went deeper than individual incident response. Autonomous vehicles would generate vast amounts of data about their surroundings, recording everything their sensors perceived as they moved through public and private spaces. This raised privacy questions about what data should be retained, who could access it, and for what purposes it might be used. The same sensor data that enabled navigation could identify individuals, track movements, observe activities visible from public roads. The potential for surveillance exceeded anything possible with human drivers who couldn't perfectly remember and catalog everything they saw. Society needed to determine boundaries around data collection and retention that balanced the legitimate needs of system improvement and incident investigation against individual privacy rights. The distribution of benefits from autonomous technology created equity concerns that extended beyond the question of infrastructure investment. If autonomous vehicles were initially expensive, they might be available primarily to wealthy individuals, while their presence on roads created changes that affected everyone. If they operated as shared fleets rather than private vehicles, they might not serve all areas equally. Economic logic would concentrate service in dense, profitable regions, while underserving rural or low-income areas where demand was dispersed. The technology promised improved mobility for people unable to drive themselves, but realizing that promise required intentional design and policy choices, rather than assuming benefits would distribute automatically. The employment effects rippled through industries beyond the obvious impact on professional drivers. Autonomous vehicles promised to reduce crashes, which would decrease demand for emergency medical services, collision repair, legal services related to traffic incidents, and law enforcement focused on traffic violations. Insurance needs would change, as fault shifted from human error to system design and maintenance. The reshaping of employment would create winners and losers distributed unevenly across society, raising questions about how to support workers whose skills became less valuable and how to share gains from increased productivity that automation enabled. The gradual deployment created transitory periods where autonomous and human-driven vehicles would share roads, each type optimized for different conditions. Human drivers might find autonomous vehicles frustratingly conservative, following rules precisely while humans bent them pragmatically. Autonomous systems might struggle to predict human behavior that violated formal rules to follow informal conventions. The mixed traffic environment could be more challenging than either pure human or pure autonomous conditions, creating a valley of difficulty during the transition that might last for decades. How society managed this transition period would significantly affect both safety during the changeover and public acceptance of the eventual outcome. The question of transparency in autonomous decision-making created tensions between competing interests. Users wanted to understand why systems made particular choices, both to build trust and to provide accountability when decisions seemed questionable. But the machine learning systems that powered many autonomous capabilities made decisions through complex processes that even their designers couldn't easily interpret. The systems learned patterns from data and applied those patterns in ways that produced good results without necessarily being explicable in terms that humans found satisfying. The demand for explainability might conflict with the use of techniques that worked best but remained opaque. The liability frameworks for autonomous vehicles required determining responsibility when systems caused harm, despite operating as designed. Should manufacturers bear liability for behavior that emerged from their design choices? Should users bear responsibility for systems they couldn't meaningfully control? Should there be new categories of liability shared across parties, including software developers, sensor manufacturers, mapping companies, and infrastructure providers whose contributions all influenced vehicle behavior? The existing legal structures built around human drivers offered limited guidance for situations where no human had directly caused the harm, but human decisions in design and deployment had created conditions that led to it. The philosophical questions extended to basic assumptions about the nature of driving itself. Was driving primarily a means of transportation, to be optimized for efficiency and safety? Or was it an activity with intrinsic value, a form of personal expression and skill demonstration that people enjoyed independent of its practical utility? The answer affected how to evaluate trade-offs between the utilitarian benefits of autonomous vehicles and the experiential losses some people would feel if human driving became restricted or socially discouraged. The question wasn't purely theoretical. Policy choices about where to allow autonomous operation and whether to eventually restrict human driving in certain contexts would implicitly answer it. The distribution of control between individuals and systems raised questions about human agency and dignity. Even if autonomous systems proved statistically safer than human drivers, some argued that people should retain the right to make their own choices and accept their own risks, rather than delegating decisions to algorithms. Others countered that choices about vehicle control affected not just the chooser, but other road users who hadn't consented to exposure to risks from human driving. The balance between individual autonomy and collective safety had no obvious resolution, touching on fundamental questions about the relationship between freedom and responsibility in social contexts. The long-term cultural effects of autonomous vehicles remained speculative, but potentially significant. Driving had shaped urban design, economic patterns, and social practices for over a century. It had been a rite of passage for adolescents, a marker of adult independence, a source of identity for enthusiasts. The skills and knowledge associated with driving represented forms of competence that people took pride in developing. If autonomous vehicles succeeded completely, these cultural touchstones would fade into irrelevance over generations, replaced by relationships to transportation that might be more efficient, but also more passive. The transition represented not just a technological change, but a shift in human capability and cultural practice whose full implications would take decades to become clear. The timeline stretched forward into decades, where the technology that seemed impossibly complex today would become mundane infrastructure, invisible in the same way that electronic fuel injection and anti-lock brakes had faded from consciousness once they became universal. The autonomous systems under development represented transitional forms, constrained by the need to operate within road networks designed for human perception and following traffic patterns optimized for human reaction times. Future generations of vehicles and infrastructure could co-evolve, each designed with the other's capabilities in mind, rather than forcing new technology to accommodate legacy constraints that had accumulated over a century of human-centric design. The roads themselves might transform once human drivers no longer determined design parameters. Lane widths could narrow when vehicles positioned themselves with centimeter precision, rather than leaving margins for human steering variability. Intersections could operate without signals when vehicles negotiated right-of-way through direct communication, rather than following fixed timing patterns designed to prevent human confusion. Speed limits could increase on routes where vehicles maintained safe spacing, and reaction times through coordination that human drivers couldn't achieve. The physical space devoted to transportation might decrease as vehicle utilization increased, parking requirements dropped, and the efficiency of autonomous traffic flow reduced the number of lanes needed to handle given volumes. The distinction between private and shared vehicles might blur or dissolve entirely. When vehicles could relocate themselves without drivers, the economics shifted toward patterns where ownership mattered less than access. A vehicle might serve multiple users across a day, summoned when needed rather than sitting idle between trips. The cost per trip could drop to levels where ownership provided little advantage over on-demand access. Urban spaces currently devoted to parking could be reclaimed for other purposes. The change wouldn't happen uniformly. Rural areas with dispersed populations might retain private ownership patterns, while dense urban cores transition to shared fleets. But the overall trajectory pointed toward transportation as service rather than ownership of depreciating assets. The land use patterns that had shaped cities around automobile access could gradually rearrange themselves. Suburbs had spread outward on the assumption that commuters would drive themselves, tolerating long commutes in exchange for space and affordability. If autonomous vehicles made commute time productive or restful rather than tedious and stressful, distance from employment centers might matter less. Conversely, if shared autonomous fleets concentrated in dense areas where demand justified their economics, urban centers might see renewed growth, while distant suburbs became less connected. The reshaping would take decades to manifest fully, but the direction of change would become clear earlier as property values began reflecting expectations about future transportation access. The environmental implications remained uncertain, dependent on choices not yet made about energy sources and utilization patterns. Autonomous vehicles could be electric and lightweight, operating efficiently through optimal routing and smooth acceleration profiles, dramatically reducing transportation's environmental footprint. Or they could enable more travel at lower perceived cost, increasing total vehicle miles and offsetting efficiency gains with higher total consumption. Empty vehicles repositioning between trips or traveling to remote parking could add miles that human-driven transportation never generated. The technology itself was neutral. Its environmental impact would depend on the regulatory frameworks and economic incentives that shaped how it was deployed and used. The capabilities might extend beyond transportation into broader reshaping of logistics and commerce. Delivery of goods could shift entirely to autonomous vehicles operating around the clock, moving packages during off-peak hours when roads were clear and demand for passenger transport was low. Mobile services could expand when vehicles didn't require drivers. Retail, dining, entertainment, medical care, all might come to customers rather than requiring customers to travel. The boundary between place and service could blur when the service could relocate itself moment by moment in response to demand patterns detected through data analysis. The generations growing up after autonomous vehicles became common would develop relationships to transportation fundamentally different from those of people who learn to drive. They might never develop the spatial awareness and navigation skills that came from years of piloting vehicles through varied conditions. They might not learn the vehicle dynamics and traction limits that drivers discovered through experience. These losses of embodied knowledge would matter to some people and seem irrelevant to others, dividing society between those who mourn the passing of driving culture and those who wondered why anyone valued skills that machines could perform more reliably. The regulatory frameworks would continue evolving long after initial deployment, responding to conditions that couldn't be fully anticipated during development. Standards for system validation and safety assurance would mature through experience with real incidents and near misses. Liability doctrines would clarify through court cases addressing novel situations. Privacy protections would strengthen or weaken based on political negotiations between competing interests. The learning process would extend across decades as society developed institutional knowledge about how to govern technology that operated autonomously in public spaces. The dream that had motivated over a century of effort, vehicles that could navigate without human attention, freeing that attention for other purposes, would finally be realized in practical form, accessible to millions of people. But the realization would bring complications that dreamers hadn't fully anticipated, creating new problems even as it solved old ones. The safety benefits would come with privacy costs. The efficiency gains would disrupt employment. The liberation from driving would introduce new forms of dependency on complex systems. The future remained unwritten in its specifics, shaped by choices still to be made about how to deploy and regulate and integrate autonomous vehicles into the fabric of daily life. The technology would continue advancing, but technology alone wouldn't determine outcomes. Those would emerge from political decisions and economic pressures and cultural values, from the ways that different societies chose to balance competing priorities and distribute benefits and burdens. The autonomous vehicles beginning to appear on roads represented not an ending, but a beginning, the start of a transformation that would unfold across generations, reshaping transportation and with it, the patterns of human settlement and commerce and social connection that transportation enables. The road ahead stretched far beyond the visible horizon, curving toward destinations that could be imagined but not yet clearly seen, promising changes both welcome and unsettling to those who would travel it. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.